All right, so this is the final video for chapter 4. And by the way, I think in the previous video, I kept saying it was a continuation of 4.2. It wasn't. It was a continuation of 4.3 central limit theorem, as is this video. So the final video in 4.3 and in chapter 4. So why don't you pause it, copy it down. That last step, it might be a little bewildering, but I'll explain that in the next panel. Okay, so the last topic we're going to discuss is how to apply the central limit theorem for discrete random variables. And what we're going to need to do is apply a continuity correction. So we need to require some care when using the central limit theorem to approximate something about a discrete random variable, because we're approximating this random variable with a normal distribution, which is continuous, whereas the random variable was discrete. And we call this care the continuity correction. So I'm going to illustrate it via an example. And I believe you might have talked about this continuity correction in 313. So I'm hoping this is sort of the second time you've been through it. But if it's not, and it's still not making sense, again, just ask me in class, we can run through another example. All right, so here's the example. We have an unfair coin. We're going to toss it 8 times and record X, the number of heads. And let's assume the coin is unfair and that heads would come up only 40% of the time, not 50% of the time. And I'd like to approximate the probability that X is 3 or X is 4. Now, I don't know why I'd want to approximate this. I can calculate this exactly using a binomial distribution of probability success 0.4 and 8 times, right? But anyway, okay. So X is clearly binomial with 8 trials, probably a success 0.4. And by that corollary to the central limit theorem from the previous video, X, the number of successes, can be approximated by a normal distribution with mean n times p and variance n times p times 1 minus p, which cranks out to those two numbers. Okay, so if I blindly start the process, I want the probability that X is 3 or 4, which means I want the probability that 3 is less than or equal to X is less than or equal to 4. And here's where I include the continuity correction. For some reason, I move 3 down to 2.5, and I bump 4 up to 4.5, right? And that's what I'm going to explain why on the next panel, which is also the final panel. Okay, so I need to edit this blue picture, but why don't you pause, copy it down, then press play. All right, so up here, I'm trying to explain the continuity correction, and I've got some detail to add in, right? So remember, X is discrete. It's a binomial random variable. So if I want the probability that X is between 3 and 4, well, 3 is less than or equal to X is less than or equal to 4, that means I want the probability that X is 3 plus the probability that X is 4. And I can illustrate those probabilities on this histograph by saying, look, the probability, I'm going to grab my PDF values, which is on the vertical, and I'm going to define the value to be the area of this bar, which has width of 1. So that area is the probability that X is 3 using the binomial PMF or PDF. And the probability that X is 4 is the area of this bar. Just keep in mind, the width is 1. I'm going from 2.5 to 3.5. And then for 4, the probability that X is 4, that's the bar from 3.5 to 4.5. So the area is a width of 1 times the height. So it's basically the area is the height, which is the probability, okay? Now, the central limit theorem says, hey, these probabilities can be approximated by a normal distribution. So I can sort of show you that normal distribution. All right, so the normal distribution is in red. Now, if I want to approximate the area in these two bars, I need to approximate the area under the normal distribution from the start of the first bar to the end of the second bar. So I need to approximate that area in red. And that runs from 2.5 to 4.5. So that's why I made the move. Instead of 3 less than or equal to x less than or equal to 4, I moved it to 2.5 less than or equal to x less than or equal to 4.5. So I've got to include the half unit extra on either side, okay? All right, and I'll do another example here at the bottom just to focus on my continuity correction, but let's complete the problem we started. So I got my continuity correction. From all 3 pieces, I'm going to subtract the mean of x and divide by the standard deviation of x. And central limit theorem tells us I can approximate that value with the standard normal variable. Left and the right side simplify to those 2 guys. And then how do we figure out the probability of z is between 2 values? I take the CDF of z of the larger value minus the CDF of z of the smaller value. And how do I calculate sigma of negative 0.5? Well, it's 1 minus sigma of 0.5. And then I grab these values from my tables and crank out my answer. Okay. All right, well, let's do another continuity correction. Assume x is exactly the same. It's binomial 8, 0.4, whatever. But let's say for some reason I wanted the probability that 3 is less than or equal to x is strictly less than 6. So this would be x values of 3, 4, 5 in the discrete binomial distribution. All right, well, if we look back up here, if I want x values of 3, 4, or 5, I'd need to start at 2.5. So 2.5 to 3.5 would give me the probability of 3. 3.5 to 4.5 would give me the probability of 4. And 4.5 to 5.5 would give me the probability of 5. And I would stop there. So I'm going to use a continuity correction to move to 2.5 to 5.5. And then replace x with its normal variable approximation. Okay. So whether or not you go up a half unit from like 4 to 4.5 or down a half unit from like 6 to 5.5 depends on whether you want to include 4 in the probability or not include 6 in the probability. Okay. All right. And again, if this isn't making sense, ask me in class and I can run through a couple more examples of this.